So today we're going to learn about exponential functions. Exponential functions are in the form f of x equals b to the x, where b is a positive real number and b is not equal to 1. You know you have an exponential function when the variable is in the exponent. The natural base is e, an irrational constant like pi. E in your calculator, if you just use, there we go, you'll notice it's 2.71828, etc. Much like pi was 3.14159, so forth and so on. Okay. So here, when we're looking at our natural exponential function, that's going to be f of x is equal to e to the x. Let's look at some examples where we go through and evaluate these. We want to write the ordered pairs. Our first one, we're going to have 5 to the x minus 1 for our function, and they want it at x equal to 3. So if I make my x equal to 3 in orange, I'm looking for f of 3, which means I'm going to be plugging in 3 wherever I see the x in my function. In this case, since we have an exponential function, the variable is in the exponent. We know that 3 minus 1 gets us 2, which means we have 5 squared. Remember, this is 5 times 5, not 5 times 2. So we get 25. And the ordered pair we just found, we plugged in 3, and we got out 25. Remember your parentheses around your ordered pair, otherwise it will be incorrect. In our next example, we have 5 times 2 to the 3x minus 4. Again, this is an exponential function because our variable is being held hostage in the exponent. We are going to plug in a 1 wherever we see an x. So we're going to have 5 times 2 to the 3 times 1 minus 4. Pay attention to your order of operations. Cannot multiply the 5 and the 2, and it should be a closed dot. 3 times 1 is 3, minus 4 is negative 1. Remember, we can rewrite that as 5 times 1 all over 2, because we would move the 2 to the negative 1 to the bottom to get it to be a positive exponent. Otherwise, if you did 2 to the negative 1 in your calculator and converted to a fraction, you would get the 1/2 that we were just discussing. And 5 times 1/2 does get us 5/2. You may be wondering, what type of work do we need to see? We need to see how you plug in your value, and at the very minimum, we need your y value. So show us how you plug it in, get your y value out. So our ordered pair in this case, we plugged in 1, so our x is 1, and we got out 5/2. Make sure that you have your parentheses around your ordered pairs and that you have your comma in between your x and y value. Example number 2. We're looking at our natural exponential function, e to the x, and we want to evaluate e to the x at different x values. So for x equal to 1, we're looking for f of 1, which means we want e to the 1. We just did e. Remember that e to the 1 is the same thing as e, but if you wanted to double check it, we get 2.7182. We're rounding to the nearest hundredth. That 8 is enough to round us up, and we get 2.72 for our y value, which means that our ordered pair is 1, 2.72. Let's see what happens at x equal to -3. This means that we need to plug in -3 wherever we see an x in our function. So we're going to have e to the -3. Let's just go ahead and adjust that in our calculator. We're not going to try to convert back to a fraction. It wouldn't work anyway. But we are rounding to the nearest hundredth. So when we look at 0.0497, oh, 0.0497, there we go. Drop the decimal, there we are. And we're rounding to the nearest hundredth again. The 9 is enough to round us up, which means that we get 0.05. And we just found our ordered pair is -3, 0.05. That is an algebra introduction to our functions. Let's go ahead and look at the actual graphs. Okay, and keep in mind that we are looking at the parent functions or the basic functions. We're not adding or subtracting anything at the end or in the exponent. It's just plain old f of x equal to b to the x. And here our base is greater than 1. And we got our graph going on to the right. Exponential functions are like polynomial functions. You can plug in anything you want and you'll still get an answer. So our domain is -infinity to +infinity. We're going to come back to the range here in a second. Ask if the graph is increasing or decreasing. From left to right, we are going up, which means that we are increasing. Let's hit our y-intercept real quick. Our y-intercept is where we cross the y-axis, and that happens at the ordered pair 0, 1. Now, the range, the x-intercept, and the horizontal asymptote. Let's look at that horizontal asymptote because that's going to help determine our range and our x-intercept. When we have our exponential functions, and it's just our base functions, we wind up having a horizontal asymptote of y equal to 0. And you can see that on our graph. We have a horizontal line that our graph gets closer and closer and closer and closer and closer to without crossing. Okay, so we know we have an asymptote, and here, since it's horizontal, it's going to be y equals, and we get close to y equal to 0. If we have a horizontal asymptote of y equal to 0, our x-intercept will not exist, D and E. And here our range, since we have a horizontal asymptote of 0, and our graph is increasing, it's going up and into the positives, 100,000, million. Our range is going to be 0 to infinity. Infinity always gets a parenthesis, and because 0 is our asymptote, it always gets a parenthesis. Asymptotes get parentheses for interval notation. The other function that we can look at is when our base is in between 1 and 0. So we have a fraction that's not bigger than 1. And notice that this time our graph is going down from left to right. Because it's going down from left to right, it is decreasing. Notice that it's going all the way to the left, all the way to the right, which means our domain is negative infinity, positive infinity. We can plug in any x value we want and still get a y value out. Okay. Our range is defined by that horizontal asymptote, and you can see we're starting to crash again or flatten out near y equal to 0. So we do have our horizontal asymptote of y equal to 0, and our range is going to be 0 to infinity because the y equal to 0 is our base or our basement, and we have nowhere to go but up. If our graph was going down, we would use negative infinity to 0. Our x-intercept, because we are not able to cross or touch the x-axis because of our horizontal asymptote, that guy still does not exist. But our y-intercept, where we cross the y-axis, is still at 0, 1. The horizontal asymptote, you may be wondering how you can figure out what it is without graphing it. It's whatever is added or subtracted after the exponential piece. Let's get into that with example number 3. Okay. It says find the domain, range, and horizontal asymptote for the following functions. We know that our domain for all exponentials is going to be negative infinity, positive infinity all the time. We know that this guy is an exponential function because the variable is in the exponent. And because we know he is an exponential function, we know that our domain is immediately negative infinity to positive infinity. Our horizontal asymptote is what we add or subtract after the exponential piece, which in this case is negative 12. That means that our horizontal asymptote is y equal to negative 12. Okay. With our range, it's either going to be negative 12 to infinity or negative infinity to negative 12. And I know that many of you will go ahead and graph this to try to find your answer. So let's go ahead and do that. We have 3 to the x come out of the exponent minus 12. Let's scan out. There we go. You can see that my graph is flattening out. at y equal to -12. So we got the correct horizontal asymptote. It's increasing. It just keeps increasing and increasing and increasing, which means our range is going to be -12 to positive infinity. Let's try our next one. We have -2 to the x plus 3 plus 6. Again, our variable is in the exponent, which means that we do have an exponential function. And if we have an exponential function, we know our domain is immediately negative infinity to positive infinity. We can plug in anything we want and still get a whole answer. Our horizontal asymptote is what we add or subtract at the end after the exponential piece, which in this case is +6. So we're going to say that our horizontal asymptote is y equal to 6. Okay. Let's go ahead and graph it so we can look at our range. Okay. Plugging in exactly as you see it. So it's -2 exponent x. Oh, let's put parentheses around that exponent. There we go. X plus 3, close the parenthesis, come down, plus 6. This time you can see that we have a horizontal asymptote at y equal to 6. So we're good there. But now our graph is plummeting down. It's going down into more and more negative y values, which means our range is going to be negative infinity to +6. Let's try our last one like this. Again, we have an exponential because our variable is in the exponent. And if we have an exponential function, that means we know that our domain is immediately all real numbers, negative infinity and positive infinity. We need to look for our horizontal asymptote next. Our horizontal asymptote, again, is whatever we add or subtract at the end after the exponential piece, which means we get y is equal to -3. You have to have the y equals, otherwise you don't have an asymptote. An asymptote is a line. And then we need the range. So if we are graphing this, we would have 1 divided by 2 in parentheses. We're going to do our exponent, and because we have a couple things going on the exponent, let's go ahead and do parentheses around that x plus 4, and then we have -3. Notice that we do have our horizontal asymptote at -3, y equal to -3. We're flattening out there. And although our graph is decreasing from left to right, our positive y values are where it's at. We just keep getting bigger and bigger and bigger, which means that our range is going to be -3 to infinity.